I'm going to work out a couple of problems now to show the mechanics of discrete time convolution. So the first problem we're going to look at is convolving a signal of the form alpha to the n u of n with h of n, which is beta to the n u of n, where alpha and beta are just two constants. I mean, alpha could be 0.9, beta could be 0.3, or alpha could be complex and beta could be complex as well. Okay, but the important thing to note here is alpha and beta are just two constants. Okay. Let's start by kind of sketching these functions and get a feel for how this convolution would work. So if I were to sketch this function x of n, this function would look like this. So on and so forth. And beta would also be a function that decays exponentially. Depending on what alpha and beta is, one may decay faster than the other. Right? So we want to convolve these two signals. The first step in performing this convolution is to think of x of n and h of n as signals with independent variable k instead of n. So let's begin by sketching x of k and h of k. So x of k is a signal which is actually going to look identical to what I already drew. But now we need to think of this as a signal with the independent variable k. And notice that the signal is 0 for all negative values of k. And for positive values of k, it's given by alpha to the k u of k, or alpha to the k. Now h of k is a signal which looks like this. Again, it's also an exponential. Maybe decays faster if beta is smaller than alpha. But this is given by beta to the k u of k, and it's non-zero only for positive values of k. Okay. Now the second step is to flip h of k about the y-axis, because that would then give us the signal h of minus k, and then we can shift this signal by n and take the product of that signal with x of k, and then integrate that for all values of k in order to get y of n. Okay, that's what we're going to do now. So I begin by computing h of minus k. Actually, I will compute h of minus k here. So h of minus k is going to look like this. So now this will be non-zero only for negative values of k. So the axis here is k. It will be 0 everywhere here. And the signal is now given by beta to the minus k for negative values of k. Right? But the whole signal is beta to the minus k times u of minus k. Just this part of it is beta to the minus k. Okay? So what is this? This is h of minus k. Now what we need to do is to take this, shift it by n units in order to get h of n minus k. So let me draw h of n minus k here. H of n minus k is simply a shifted version of h of k here. It will be shifted to the left if n is negative, and it will be shifted to the right when n is positive. Okay. So what happens when n is negative? When n is negative, I'm going to take this signal. Notice that it starts at 0. And then I'm going to shift it to the left. So I may end up with a signal like this. For example, if I shift it by 2 units to the left, I will end up with a signal like this. And when I form this intermediate signal Wn of k, which is the product of x of k and h of n minus k. Now the important thing to note when you perform convolution is this. This intermediate signal will take different forms for different values of n. Mathematically, it may be expressed by different functions for different values of n. The skill that you really need to acquire, or one of the skills that you need to acquire, is to be able to figure out what this function is for different ranges of n. You sort of have to look at the problem and be able to figure out, okay, in this range of n, Wn of k can be written by this particular expression, and this expression would hold for n in this entire range. Okay, but remember, n should just be treated as a constant, and Wn of k is really a signal with independent variable k. Okay, we will take the summation over k of Wn of k in order to get y of n. Okay, and you will see as I proceed in this problems how some of this works out. So now if I look at it, I know that for all negative values of k, h of n minus k and x of k are not going to overlap with each other at all. In other words, h of n minus k is going to start only from time n equal to minus 1 for all, k equal to minus 1, I'm sorry, k equal to minus 1 whenever n is negative. So for all n less than 0, Wn of k is 0. Because it's the product of two of them, and one of them is always 0 for all values of k if n is negative. So this means that y of n is 0 for all n less than 0. Okay? Okay. Now as I start to shift h of minus k for positive values of n, or 0 or positive values of n. So let's look at h of minus k. H of minus k is a signal. Let me draw it again. So zeros here. This is beta to the minus k. Okay. Now this is how h of minus k looks. I just got interrupted by someone, so I had to pause the video while I was making it, and now I forgot what it is that I said last. I think we were trying to compute h of n minus k when n is positive. Yeah. So when n is positive, what happens is we take h of minus k and we shift h of minus k to the right by n. So when we do that, what's going to happen is this whole signal gets shifted to the right. Let me see if I can draw this in a different color, just to I don't know how to pin options. Maybe I should keep this somewhere. It doesn't matter. So what happens is this signal gets shifted to the right. So the new shifted signal is going to look like this. It got shifted by n to the right. So this is now n. Notice this is important. This is n. And what is this signal now? This signal is actually beta to the minus k minus n, which is actually beta to the n minus k. Okay. Now what we need to do is we need to multiply these two signals together. When I multiply these two signals together, I have to multiply pointwise. I'm going to multiply this with this, this with this, so on and so forth. And that is what gives me my wk of n. So for n greater than 0, w sub n of k is going to be the product of these two. So when I take the product of these two, what's going to happen is this. For all values of k bigger than n, so look at all values of k bigger than n, which is all these values of k. This signal is 0, right? This is all 0. So wn of k is going to be 0 as well. Similarly, for all negative values of k, wn of k is going to be 0 as well, because the first signal, x of k, is 0. So wn of k is 0 for k less than 0. It is also 0 for k greater than n. So for values of k between 0 and n, it's given by the product of this and this, which is alpha to the k times beta to the n minus k. Okay. Now in order to find y of n, we need to sum wn of k for values of k from minus infinity to plus infinity. But I just figured out that wn of k is 0 if either k is less than 0 or k is greater than n. So this summation can be written as summation from 0 to n, alpha to the k times beta to the n minus k, which I can write as beta to the n times summation 0 to n, alpha to the k times beta to the minus k, which is actually the same as alpha over beta to the k. And now you will thank me for emphasizing the importance of being able to sum consecutive elements of a geometric series. Okay, because this is sum to n terms of a geometric series, starting from alpha over beta to the 0 and going up to alpha over beta to the n. So the ratio of two adjacent terms in the geometric series is alpha over beta. So the answer then is beta to the n times 1 minus alpha over beta to the n plus 1 divided by 1 minus alpha over beta. So this you can simplify into, so what I have is a beta to the n plus 1 minus alpha to the n plus 1 divided by beta to the n plus 1 times beta minus alpha over beta. So I can remove this, and then I can remove this and this, and I get a nice form which says this is beta to the n plus 1 minus alpha to the n plus 1 divided by beta minus alpha. So the final answer is this. The final answer is that y of n is 0 when n is less than 0. When n is greater than 0, it's beta to the n plus 1 minus alpha to the n plus 1 divided by beta minus alpha for n greater than 0. So that's the final answer. Okay.